All right, today for geometry, we're going to do 2.1, which is inductive reasoning. All right, so our objectives today, we're going to make conjectures based on inductive reasoning. And so inductive reasoning, let's just go ahead and talk about that, is, so we got here inductive reasoning. It's the process of coming to a conclusion by finding a pattern in several specific examples. Okay, so we're going to come to a conclusion by finding a pattern in several specific examples. Okay, the conclusion that you reached is called a conjecture. All right, so a lot of geometry is based on inductive reasoning. Okay, so we're going to look at something, and it may not always be a pattern. We're going to start out with some simple patterns, and then later proofs and different things or things that we know about shapes, we're going to use those and find patterns in those to make a conjecture. Okay, so inductive reasoning, we're looking at something and coming to a conclusion by looking at these things. In this case, it's talking about patterns. All right, then our other objective is we're going to use counterexamples to disprove statements. And we also want to recognize that the lack of a counterexample does not prove a statement true. So just because we can't come up with a counterexample doesn't mean that it's true. Other people might be able to do the counterexample. Okay, so let's look at example 1 and see what we can come up with there. Okay, it says make a conjecture describing the pattern in each series of examples. Then find the next two terms in each series. All right, so example A there, classes beginning at 8:15, 9:05, and 9:55. What can we notice about those so we can make a conjecture? Because we do want to find the next two terms. Okay, so how long is it from 8:15 to 9:05? Well, 50 minutes, right, has passed. So then does that hold true for 9:05 to 9:55? Yes, we have another 50 minutes. So to come up with our next two terms, we're going to have to take 9:55 and add 5 minutes to that, which would make it what time? Excellent. So it would be 10:45, and then another 55 minutes would make that, excellent, 11:35. So you just use inductive reasoning, okay, to look at that pattern and draw a conclusion. Okay, B, that may be a little more difficult for some of you to find the pattern there and how it's growing. So always look at what you know. So if you start off here, like in pattern 1, you just have this one dot. Okay, in the first term, you have one dot. Okay, in the next one, you still have the same dot, but now you have another row and it has 2 in it. And then in the next term, you have that first dot, you have those same 2 dots for the second row, and suddenly you have a third row of 3 dots. And so you have 6 dots total. And then for your last one, you are starting to see the pattern. So we have 1 dot. Let me change my color. Then we have our second row of 2 dots. Our third row has 3 dots. And so our fourth row is going to have 4 dots. Okay. Now, in this example, it kind of depends on what you have to do. It says find the next two terms. If you're just looking here, like what am I doing? How am I getting from 1 to 3? Well, I added 2. From 3 to 6, I added 3. From 6 to 4, I add 4. You're also recognizing another pattern. So you know the next time you're going to have to add 5, and then you'll have to add, great, 6. So you could know how many numbers are in each pattern. So 10 plus 5 is 15. 15 plus 6 would be, good, 21. So if you just had to say how many were in the pattern, that's fine, but maybe you also had to draw it. Okay, so if you had to draw it, like 15, you'd have 1, and then you'd have your second row of 2, and your third row of 3, and your fourth row would have 4, and your fifth row would have 5. dots. And then you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. For your next pattern, you would draw that out again. I'm going to draw it up here. So I have my one row of 1, my second row of 2, third row of 3, fourth row of 4, fifth row of 5. Now I need a sixth row that's going to have 6 in it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 indeed. Okay, so not only do you know the number that you should have, you can actually draw the pattern. Again, inductive reasoning. All right, how about C? How about C? What do you notice is happening here? There's maybe a couple things to notice here. Okay, in this first diagonal, or this first box, we have a solid diagonal, and in the third one, we have a solid diagonal. But in the middle one, we have a dashed diagonal. Okay, and then we've got some shapes to think about. So we have a circle in the bottom left corner on the first piece, a circle in the top right corner, and then no circle. Okay, then we have a triangle in the top right circle here, no triangle, and here the triangle is in the bottom left. And our last piece, or our last one, is a square. We don't have a square inside this one. We have a square on the, oh, I tried to switch colors, I didn't make it. We have a square in the bottom left here, then a square in the bottom right here. So we've got these three shapes, right? Like this one, I'm gonna draw the square out here because there was no square. In the second one, there's no triangle. In the third one, there's no circle, okay, because they're out. So can we determine what the next pattern would be? So we've got this square box. So if I look at my diagonals, what should my diagonal look like? It should be dashed, right? Should be a dashed line. Okay. And how are my shapes moving? So my circle went from the bottom, right, to the top, and then out. If we want to look at it that way, right? The circle went bottom, top, and then out. It's not there. The square looks like here we've got the square. It's at the starts at the bottom, and then it goes to the top. So the square should be out of this one. The triangle here is at the bottom, so where should it move to? Our pattern's been bottom, top, out. So if I'm at the bottom, it should go to the top now. So I should have a triangle here. I should have the square out, so I should have my circle coming back in. Then I need another pattern. Okay, what about my diagonal this time? Good, it should be solid to go with the pattern. My circle should move up to the top right. My triangle should move out, and my square should move in the bottom left. So there would be my next two in the pattern. Okay, so this is just inductive reasoning, okay, because this is what geometry is all about. It is looking at something and drawing conclusions from what you can see and what you know. The other thing is, though, you have to learn a lot to know things to be able to draw the conclusions. So that's what we have theorems or why we have proofs. Okay, proofs are showing us what we know. We have theorems and postulates that tell us what we know. Proofs are where we show the conclusions that we are making and we're showing our reasoning, but we have to learn the theorems and the postulates to be able to make those conclusions. That's where the hard work comes in. Okay, because it's a totally different, it's like logic and math smashed into one for geometry. All right, example 2 says make a conjecture describing each instance. So number 1, or sorry, 2a there, the product of an odd and an even number. Okay, so we want to make a conjecture. So that means we need to come up with some examples here. The product of an odd and an even number. So you just start picking some. Okay, we've got an odd and an even and its product. So maybe we say 3 times 2. Okay, well that's 6. 5 times 8. All right, well that's 40, right? Odd and even. So maybe we have 5 times 4. That's 20. I was going to write 7 and then I wrote 2, so let me go back here. How about if we do 7 times 2, 14. All right, 3 times 10, 30. You could keep going as long as you need to. Okay, but you're showing me some work here. Now, what's a conjecture that you can make based off of all of these products or all of these answers? What's a conjecture that you can make? Okay, so maybe you've noticed that all of these numbers are even, right? So we could say, hey, it appears, because we're not for certain, but it appears the product of an odd and even number is an even number. That's what we could say about that. That's the conjecture that we can make. Okay. How about B? The sum of the measures of the angles in a triangle. That's a little bit harder to do up here if you had a protractor, okay, and it would make it a lot easier. So, because what you would need to do is draw a variety of triangles. So let's say I have this triangle, all right, and I've got 90, I measure it here, and I've got 90 degrees here and 32 degrees here, and oh, that's, let me undo that. That wasn't the number I wanted to write. So we've got 90 there, and let's say this is 46 degrees, and this is 44 degrees. Okay, so we've got that measurement. Then I draw a triangle that looks like this, and this angle is 60 degrees, and this one is 58 degrees, and this one is 62 degrees. Okay. And I draw another angle. Maybe I want like a really wide one like this. Okay, and maybe I have this angle here is 162 degrees. And this angle here is 12 degrees. All right, and then this angle here is 6 degrees. Okay, but the question is asking us to draw some conclusions about the sum of the measures. Okay, well the sum is when I add these all up. So what is 90 plus 46 plus 44? Oh, it's 180 degrees. Okay, how about here? What's 60 plus 58 plus 62? Oh, it's 180 degrees. All right, how about what's 162 plus 12 plus 6? Oh, it's 180 degrees. All right, so what conjecture can I make about those? It appears, I should have spaced those out, I'm sorry. It appears the sum of a triangle's angles is 180 degrees. Again, it appears to be that. It's not necessarily true. That's just what it appears to be because it's a conjecture. All right. So a pattern isn't always guaranteed to continue, however. Consider, like if we think about example 1, okay, and the school schedule, consider having a 30-minute lunch in there. The class start time would alter from the pattern. Okay. So maybe you do have your first 5 classes and the same pattern, and then you have lunch and things change. That's kind of what happens here. So this is a counterexample. It's an instance that proves, counterexamples will prove a conjecture false. Okay, just because we don't have a counterexample doesn't mean it's not false. But if we do have one, it proves the conjecture false. All right, so let me clear this up. And let's look down here at example 3. So after examining the listed products, Jen concluded that every multiple of 3 is odd. Give a counter example to show that the conjecture is false. Okay, so she's got these examples. 3 times 3 is 9, 3 times 9 is 27, 3 times 15 is 45, 3 times 27 is 81. Give us a counter example to show that the conjecture is false. Well, that might be a little bit easy because we just talked about how odd number times an even number, okay, earlier, so maybe that would help you. But yeah, if we look at this, 3 times 2 is 6. That's an even number, so could be a counter example. You could put any of them. 3 times 4, that equals 12. It's a counter example. Okay, it shows that the conjecture that Jen drew is false. Sometimes they're a little bit harder to come up with, but they're going to be really helpful. Okay, Joseph claims that the function f of n, I should have added a table here. I've got that note to myself. Yours will have one in there, but I can draw mine. Joseph claims that the function f of n equals 1/2 n cubed minus 1/2 n squared plus 2n minus 1 can be used to find the sum of the first n squares. Give a counterexample to show that this conjecture is false. Okay, so this might be a place where it's a lot more work to do this. Okay, so he's claiming that the function f of n, so the function of some number, can be used to find the sum of the first n squares. So we have to understand the question a little bit first. But, so what we're going to do is I'm going to add this table in there, okay, that's going to have our n in it, and it's going to give us some workspace for this equation. 1/2 of n cubed minus 1/2 of n squared plus 2n minus 1. And we're going to see if that comes up and equals the sum of the first n squares. All right, so our first number is going to be 1. Okay, which means we're going to say, well, 1/2 of 1 cubed minus 1/2 of 1 squared plus 2 times 1 minus 1. Okay, so notice I'm putting the 1 in, my n, for each place that I have n here. So 1/2 of 1 cubed is just 1. So let's see. 1 cubed is 1, so 1/2 of 1 is 1/2 minus 1 squared is 1. 1/2 of 1 is 1/2. 2 times 1 is 2, and then we have minus 1. So 1/2 minus 1/2 is 0. 0 plus 2 is 2. 2 minus 1 equals 1. Okay, so this equals 1. And the cool thing here is 1 squared equals 1. So these two numbers match up. That's an example, not a counterexample. All right, so we're going to move on to 2. So we're going to say 1/2 of 2 cubed minus 1/2 of 2 squared plus 2 times 2 minus 1. Because again, we're plugging our value, this 2 value, in for the variable every time. So 2 cubed is 8. 1/2 of 8 is 4. Minus 2 squared is 4. 1/2 of 4 is 2. Plus 2 times 2 is 4 minus 1. 4 minus 2 is 2. 2 plus 4 is 6. 6 minus 1 equals 5. All right, so we want the sum of the first n squares. So we're talking about 1 and 2 here. So we're going to say 1 squared plus 2 squared equals, well, 1 squared is 1, 2 squared is 4, 1 plus 4 is 5. All right, so we have another example. Okay, it might take us a while to get to a counterexample, unfortunately. But do you just want to like jump around? I don't know. Like we could. and see what we get? Do you want to jump around or you just want to keep going? I can't really hear you, so we're just going to keep going. There's something to be said for that. All right, so we're going to have 1/2 of 3 cubed minus 1/2 of 3 squared plus 2 times 3 minus 1. Okay, 3 cubed is 27. All right, so half of 27 is just going to be 27 halves. I'm going to leave it. 3 squared is 9, so 1/2 of 9 is going to be 9 halves, plus 2 times 3 is 6 minus 1. So 27 halves minus 9 halves. 27 minus 9 equals 16, right? So that would be 16 divided by 2 is 8. All right, so 8 plus 6 equals, hold on, is that right? 27 minus, oh, no, 27 minus 9 is not 16, it's 18. My bad. So 27 minus 9 is 18. 18 divided by 2 is 9. 9 plus 6 is 17. Oh my gosh, I cannot do math today. 9 plus 6 is 15. 15 minus 1 equals 14. Yikes. Sometimes that happens, right? You have those non-math days. And I know that you aren't sitting here watching me, but I still make math mistakes, okay, when I'm at the board. All right, so then the sum of the first n squares. Now we've got n as 1, 2, and 3. So we're going to add all those. 1 squared plus 2 squared plus 3 squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 1 plus 4 plus 9 equals 14. Another example. We're going to keep plugging away. We'll get there. So next up is 4. So we're going to have 1/2 of 4 cubed minus 1/2 of 4 squared plus 2 times 4 minus 1. All right, so 1/2, 4 cubed, first of all, is 4 times 4 is 16, right? 16 times 4 is 64. Yeah, so half of 64 is 32, minus 4 squared is 16, half of 16 is 8, plus 2 times 4 is 8 minus 1. All right, so 32 minus 8 plus 8, well, that's kind of cancel, so I'm still sitting at 32. Minus 1 equals 31. All right, and so now the sum of these, and honestly, you can take the shortcut, right? Because 1 squared plus 2 squared plus 3 squared is 14. So we can just do 14 plus 4 squared. Hopefully that makes sense to you. We're just taking the number here. Like here we could have done 5 plus 9 was the 14. Because there's the pattern. 1 plus 4, 1 plus 4 plus 9. 1 plus 4 plus 9 is 14 plus the 4 squared. All right, so this is 14 plus 16, which equals 30. Hey, we just found our counterexample right here. This is it. That is no longer true. We took it far enough that we can disprove this conjecture, or we can say this conjecture is false, because we have a counter example, right? This is our counter example. It's proving the conjecture false. All right, that is it for 2.1 and using inductive reasoning there. So hopefully that is helping out, and I'll see you later.